Solve y1 prime equals 5y1 minus y2 and y2 prime equals 3y1 plus y2. To start this problem, I'll write it in matrix form as y prime equals the matrix 5, -1, 3, 1 times y. Now, since this is a homogeneous linear system, I can find the general solution using the eigenvalues and eigenvectors of the coefficient matrix 5, -1, 3, 1. To find the eigenvalues, I need to solve the determinant 5 minus lambda, -1, 3, 1 minus lambda equals 0. So I need to solve 5 minus lambda times 1 minus lambda minus -1 times 3 equals 0. Rewriting the equation, I get 5 minus 5 lambda minus lambda plus lambda squared plus 3 equals 0, or lambda squared minus 6 lambda plus 8 equals 0, which factors as lambda minus 2, lambda minus 4 equals 0. So the eigenvalues are lambda 1 equals 2 and lambda 2 equals 4. These are distinct real eigenvalues, so the form of the general solution will be y equals c1 v1 e to the lambda 1t plus c2 v2 e to the lambda 2t. Next, I need to find the eigenvectors v1 and v2. So I need to solve 5 minus lambda, -1, 3, 1 minus lambda times x1, x2 equals 0, 0. Plugging in lambda 1 equals 2, I get 5 minus 2, -1, 3, 1 minus 2 times x1, x2 equals 0, 0. So 3, -1, 3, -1, x1, x2 equals 0, 0. So 3x1 minus x2 equals 0. So x2 equals 3x1. Choosing x1 equals 1, I get x2 equals 3. So one eigenvector corresponding to lambda 1 equals 2 is the vector 1, 3. Repeating for lambda 2 equals 4, we get 5 minus 4, -1, 3, 1 minus 4 times x1, x2 equals 0, 0. So 1, -1, 3, -3, x1, x2 equals 0, 0. So x1 minus x2 equals 0, x1 equals x2. So if x1 equals 1, then x2 equals 1. So one eigenvector corresponding to lambda 2 equals 4 is 1, 1. Putting our eigenvalues and eigenvectors into the form of the general solution, we get that y is c1 times v1, the vector 1, 3, times e to the lambda 1t, so e to the 2t, plus c2 times v2, so the vector 1, 1, times e to the lambda 2t, so e to the 4t. This is a perfectly good answer, but if we want to write the general solution as two separate functions instead of in vector form, we can by saying that y1, y2 is c1, 1, 3, e to the 2t, plus c2, 1, 1, e to the 4t, which we can then write using scalar multiplication as c1 e to the 2t, 3c1 e to the 2t, plus c2 e to the 4t, c2 e to the 4t, and then by matrix addition, we get c1 e to the 2t plus c2 e to the 4t in the first component, and 3c1 e to the 2t plus c2 e to the 4t in the second component. So y1 is c1 e to the 2t plus c2 e to the 4t, and y2 is 3c1 e to the 2t plus c2 e to the 4t. It's worth noting that even though c1 and c2 are arbitrary constants, when solving systems you should never absorb constant multiples like the 3 in the y2 equation into the arbitrary constant, because an important part of the solution is the ratio between the coefficients in the two equations. And if you try to absorb a constant into one of the arbitrary constants, you change the value of the arbitrary constant and lose the information about the ratio.